All right, let's get started. Welcome, everyone. I'm going to talk today about the big question you see on the screen for the entire time already, and that's to see if you're really sure that your access tokens are really secure. At some point, you will see some QR codes. You will see this one again. This just links to my socials if you want to grab them. But there will be another QR code at the end, which you can scan to get this presentation already, if you want to. Let's dive in. So we'll begin with a story based on true events. There once was a team who delivered an API system that was publicly available. It had to interface with other systems, and people could subscribe to that API and pay them for resources and blah, blah, blah. And of course, to secure the API and to make sure that only specific customers had access to that API, they used Jwt access tokens. And because security is hard, I think we can all agree on that part, they used a well-known library to validate the Jwt tokens, to see if the Jwt tokens were correctly structured and everything. They also used a trusted third-party identity and access token management system. It was a well-known company. They paid a lot of money for those systems so that they know that the one issuing the tokens, we can trust those as well. Also, they diligently checked their code base to see that everything was configured correctly. So they only had that one issuer to go for the tokens. They had the correct validation logic and everything else. So they only trusted tokens that were issued from that trusted party. And then, of course, every token needed to have a valid signature. And everything was good. Everything worked. Customers were happy, they could access their data, and everything was secured. But then, at some point, disaster struck. After running the API in production for a few months, customers started filing complaints saying, hey, we're losing data and we don't know why, how, or we see that our data is being modified and it wasn't us or our systems. What's going on, guys? And of course, the team immediately started to investigate what was going on with their system, and everything looked fine, everything looked normal. Someone thought that it had to do with containerization, or deciding to split up the application into microservices, or the orchestration wasn't working correctly, or events went missing, or something got jumbled up in the flow. It was really the blame game, because the people were like panicking. They didn't know what was happening. And at some point, a team member, let's call them Morgan, for the sake of the story, had the bold idea to temporarily increase the log events. So they said, I'm going to start logging everything, even those access tokens. And the team was like, dude, this is like sensitive information. You can't just log these things. And he said, look, we don't know what's going on. We are losing customers. Let's log everything, including the tokens. We'll do it for a week, and then we revert back. And after investigating some of these tokens, the team was glad that they took this decision to actually log them as well. Because they were seeing some tokens that made it through that validation logic, and they shouldn't have. They should have been blocked. Before I continue with the story, let me tell a bit about myself first. I'm Wesley. I work at NDC Software as a customer success engineer. I used to be a consultant, but then I jumped ship. I love coffee, but not as much as I do love my beers. And then again, the social links are there as well. And also, before continuing with the story, let's quickly recap what a Jwt is, what a JWT is. So, most JSON Web Tokens that you see in the wild, they will have 3 sections, each separated by a dot. And the first section is the header. It tells you the structure of the token, and then we have the payload, and then we have a signature. And the header and the payload will be JSON objects, hence the name JSON Web Token, and then the signature is a cryptographic result of an algorithm. And technically, tokens can contain additional parts if you're also using token encryption. But for the purpose of this session today, we're not going to focus on encrypted tokens. We're sticking with signed tokens only. There's also, actually, we call all of these JWTs or GWTs, but actually it's more correct to say either GWS or JSON Web Signature for signed tokens, and GWE or JSON Web Encryption for encrypted tokens. And I seem to sometimes drop the microphone. Now, in that header, that tells the application what type of token it is, what kind of signature algorithm is being used, and then also the key identifier so that the application can check this is the key used to sign the token, this is the same key I need to use to validate the signature. That's what you typically see there. Could be more in there, but this is typically always there. In the payload, we have information about who the token represents or which client the token represents. So we have various claims like the subject ID, client ID, maybe your name, your email, depending on what kind of token it is. It could also contain scopes to say what you can access in an API or resources. And there's also a set of token validation parameters in there, like the issuer of the token, when the token is valid, until what time it is valid, and so on. And then the signature, again, is a calculated byte array and the result of a cryptographic function on the header.payload so that it is a tamper protection. So if you would tamper with the header or the payload, the signature becomes invalid. And this is what a JWT looks like. Most people may have already seen this. You can clearly also see that the signature bit, that's the blue part at the bottom, it's clearly not intended to be human readable. People will probably also say that about the first two parts, but that's because they are base64 URL encoded to make it easier to send them over the internet. Because in the beginning, a lot of tokens were being sent in the query parameter on the URL, and then we needed a way to send those safely. But the first two parts can be very easily converted back into a JSON object so that we can now see what's inside of the actual token. In this example, we can see that the header says that the token is signed with the ES256 algorithm. It is a type @ plus JWT, which means it's a JWT token and it's an access token. And then you also see the key ID that was used to sign that token. And in the payload, you can see my subject ID, my name, the issuer of the token, what scopes that I can do, and then some other claims like it was issued at that epoch time, it expires at another one, you cannot use the token before another time. And then you also see GTI, which is the unique identifier for this token. That's something that libraries can use to prevent replay attacks. And then at the bottom, you see the result of the signature that was generated using that ES256 algorithm. Let's go back to the story. What was happening with those tokens? What did Morgan find? Well, let's play a game called Spot the Dot. I will show you 3 tokens, and 2 tokens will open the door normally, and 1 token opened the door in a malicious way. So these are the 3 tokens that we're going to investigate. And something was very disturbing about one of these tokens. It is a bit difficult to spot on a slide, so let's mark where the dots are. And now it's going to be fairly obvious that there's something very, very wrong with the second token. There's a dot at the end. There should be a signature behind that dot. What's happening with that token? Well, let's take a look, shall we? If we decode that token, we'll see a header and a payload, and then no signature, because there is nothing behind that second dot. And you see algorithm none, which means no signature algorithm. We also see that the evil person has given themselves admin scope. I do hope that you do not do this in production, that mechanism to give yourself admin access to an API. But in this example, they weren't the best at securing their API. But we see someone crafted a token and said, hey, I'm going to set algorithm to none. I can do whatever payload, and then I don't need to sign it. So let's see if that token got accepted. And apparently, it got accepted by the API. And it should have been rejected by the validation library. So again, algorithm none means no signature algorithm being used, and it is a valid token. If you read the RFC, algorithm none is completely valid, which also means, in theory, that your API should accept it. You probably don't want to do that. And they investigated this. They actually tried it themselves, and the validation library was rejecting tokens where algorithm equals none. However, it failed to detect algorithm equals none in caps or mixed case. I am not making this up. This actually happened. If you really want to know, it was a Java library. I can tell it here. It's a .NET conference. So yeah, that meant their API was wide open to attack. But fortunately, this was very quickly fixed. But wait, there's more. So the team, of course, said, oh, we didn't catch this, but now it's fixed. They rolled out an update. They informed their customers. Everyone was happy. But they didn't get to relax for long, because a few weeks and months after, yet another series of strange events started to happen. And of course, with the past experience, the team now said, let's start looking at those tokens first again, because this is exactly the same as before. So they started logging the tokens again and started investigating them. And this was one of the tokens that got through and shouldn't have. Now, this time, we can clearly see there is a signature. So at first glance, there's nothing wrong. Let's put this token next to another token that should have been accepted. And I took only the header, because I already know what's going on, of course. And you see, this is a header from a good token on the right side, and on the left side was a malicious token that got accepted. And clearly something is wrong here, because it's way larger than the other one. Anyone have a clue why that could be? Don't worry, they didn't have a clue either. If you decode that header, you can see algorithm ES256, which is what they expected, type access token plus JWT, there's a key ID, and then there's something else, another JSON object. There's a GWK claim with properties like CRV, key ID, which is the same as the other one, KHCI, key type, an X and a Y value. In short, This is the public part of a key, or from a JSON web key, used to, someone else has the private part and signed the token, and then injected the public part in the token and said, hey, here's a JSON web key for you, and here's the key ID that I used for signing the token, and oh, by the way, it's the same key ID as the public key that you have here, so go ahead and use that to validate the token. And the team was like, wait, what? So there is an RFC, 7515, that says, hey, you can self-sign tokens. So if you want, you can add into the header the GWK claim with an integrated JSON web key JSON object, or a JKU claim, which is a URL pointing to a set of JSON web keys. Or you can do it the old-fashioned way and just insert certificates. So you can have an X5C claim with a certificate chain, or X5U claim with a URL to a certificate chain. And I still have to find a valid use case for this. One could be if you use encryption, then you can sign the token perhaps and include the key material, but you encrypt it with private public key material and then keep that separated. But other than that, I really can't think of a valid use case for using this. And the team was really a bit annoyed by this because everything that they saw was valid. Valid algorithm, valid signatures. The only problem was they couldn't just block the key ID that they saw to only trust the key ID that they have. They had to build logic to say, if a token is signed with a key ID and that kind of algorithm, let's first look at our known key IDs to see if it's one of those, and not just accept any key ID. And they started writing tests to everything that they were now doing to improve the security of the system. They were also writing tests to mimic whatever the attackers were doing, to validate that their fixes were stable, which is a very good idea. Now, you also need to ask yourself, what JWT validation library are you using? There are a lot of them. I think most of us, who's doing .NET? Everyone apparently in the room, cool. Who's doing Java? A few, brave souls. Go, Rust, someone? Okay. So there's a bunch of validation libraries for all of these languages and frameworks. Most of us in .NET will use system identity model ... or Microsoft identity model ... But there are different ones if you need to do something more secure, because those only implement the basic, well, not basic, but the feature set that 99% of the world uses. If you want to be on the cutting edge, there is a different library that you can use as well. If you go to that URL, you will have a complete list for different languages. And then you have a feature set, this one can do this one can do that. But can you trust the library? Or even should you trust the library? I mean, system identity model, even though it's Microsoft, it is open source. It has been open source for a while. So that means you can look at the source code and see what's going on. And in this case, Microsoft will also be very diligent in checking if you do a pull request that you don't try to inject malicious code in there. But there was also a recent problem with a bunch of NPM packages that were injected with crypto stealing code. So that's the downside. You have to be really diligent in open source to block malicious attempts to make your library do something different that you want to do. You can go for a vendor library, although I don't even know that there's a paid solution for validating tokens at the moment. This also means that you probably won't get access to the source code, and you just have to place your trust in them. Or updating. Do you update regularly all of your NuGet packages or npm packages? If you update, do you also test everything to ensure? I see someone nodding, but I see nodding in yes and no. So you should really check everything updates to see if it doesn't introduce something new. And of course, package feeds can also not be trusted. Again, someone was doing a targeted phishing attack at various npm authors to gain their credentials and started pushing packages in their name to the feed. So I say trust but verify, which is a typical good thing to do in security. So as I was also working with APIs and access tokens, I was writing these tests. And I found that I was quickly repeating myself because a lot of these tests are very similar. So let me show you real quick how you can do some integration tests to validate JWT access tokens and also to catch these weird things that were happening. Let's see. Maybe this is not the best theme for presentation. Oh, that better? Is it readable, the text, for everyone? So I have a bunch of tests here, and I wonder if I can zoom in. That was not the zoom in I was looking for. No. But you can see the tests, right? And all of them are green. I'll rerun them for you. All of them are green right now. And I have a bunch of tests. I have a test that says, hey, whenever a token comes in, we're only going to allow specific audience claims in there, or we're going to expect a specific issuer. And then if something is good, we should see a successful response. In this case, it's not a 401. But if it's an invalid token, we should expect a 401 to be returned. I also have tests to check the token type parameter, so it should always be AT plus JWT for me. I also test the signature algorithms. So in this case, in this API, I'm saying I'm supporting all of these signature algorithms, so ES 256, 384, 512, and PS the same numbers, but I'm not allowing the following algorithms. HS 256, 384, 512, which is public key signing of tokens. RS, because it's a bit older. And also, I do not allow none in lowercase, none in mixed case, and custom. And you can see right now that the validation is successful. So if someone tries to use a token with none in mixed case or custom as a signature algorithm, then my API will not accept it. By the way, this is by default in .NET. But it's not bad to have a test to actually verify that an update doesn't break that behavior. You can also see that I have external signature tests. And this is for those self-signed tokens, I'm verifying if you use an external certificate by specifying the X5C, X5U, JKU, and GWK claims, my API should return a 401. So it doesn't accept self-signed tokens. And this is probably the most interesting case to look at. So I'm setting up some tests, and I have a shared base test class. But my test is fairly easy. So I get a JWT token for a specific test case, In this case, I'm going to use a JSON web key hosted on a URL. Then I set that token to my HTTP client. I do a get async of my target URL, and I should assert that it's an unauthorized response. Of course, there's a lot of logic behind the scenes. So if I go to that get jot method, I have to do some mimicry where to see what kind of algorithms are actually allowed. So that if I generate a token with a self-signed signature, I'm using a signature algorithm that is actually supported by my API. And then I create my jot token and I sign it. And I either inject a JSON web key, use an external one, and so on and so on. I will not go into the details of this because that would take me probably the remainder of the session. But again, if you do this once, this is a fairly good test case for using it everywhere in every API. Which is why I made a template out of this. So if I go to Jwtguard.net, I have no internet. Great. Quickest way to fix that is to tether to my phone. That's what you would think. There we go. So Jwtguard is a open source, again, trust but verify. I wrote this, I trust myself. You may want to, you may decide not to, but the code is there, you can see it. All that this does is, it's a NuGet package, which you can install on your PC using .NET New install, and that adds templates. So whenever you do .NET New, or in Visual Studio you say File New Project, you will now see Jwtguard as the option. And then you can add the Jwtguard project to your solution, and this is just an integration test project. So it contains all of those tests, and then you need to do some settings for the target URL, for example, and then most of it will run. So this is how you use it, and this is how you configure it. Again, I'm not going to go into the full details here. This is homework for you if you want to do this, but it's there, and I use it. It's a good thing to have. But let's do something wicked now. Let's see if we can break our tests. If I go into my API code, you can see this is like the default API that you generate in C# with the weather forecast URL. But it has been set up to use authentication and authorization. So whenever you go to /weather forecast, there should be a valid token. And that has been configured with the typical add authentication, add job bearer, and then I set some options. So my authority goes to our demo identity server at doingthissoftware.com. My audience is API. I have some valid algorithms, so I only allow these signature algorithms to be used. The issuer should be demo.doingthissoftware.com. The token type should be AT plus JOT. I require an audience, and so on and so on. Now, I already added some code here to allow some special cases. And if I uncomment this, I will dive into the code in a second. If I now run my tests again, four have failed, which means someone tried now to use a token containing, for example, the X5C claim to self-sign it, and this time my API gave a 200 OK response. It was accepted. What happened? So what I did is, in my validation logic of the tokens, I said, whenever you need to find the signing key, use this method to do so. By default, it will look at your authority, it will try to find the .well-known OpenID configuration, which contains a URL pointing to the JSON web keys, and that will be used to find your keys. But you can have your own logic, and I did that. And this logic we'll see. So I have a token, I'm getting the header, and if that header contains a GWK value, that's a JSON web key, use that. Very bad idea. If it contains a GKU claim, then let's create an HTTP client, go to that URL, get the string, and that's a JSON web key set, and use those. Please don't try this at home. I mean, you can try for investigating stuff, but this is how you open up your API for attacks. A better way would be to, I would not allow this at all, but you could have valid use cases for JKU or X5U, but then don't just go out and fetch the data. First, verify that it's coming from a source you trust. And I'm not doing that here. So I can now generate a token, inject it, and it works. Of course, the solution is very simple. To fix this, don't do this. All right, so let's head back to the slides. Again, Jwtguard, open source. I still have to update it to .NET 10, but I'm waiting for the final release. I didn't bother for .NET 9 because you can just upgrade this very easily yourself. Because you also, that's the beauty of this project. It's just a template. So while you could update it, and I could update it with more tests, once you roll it out on your PC in your project, the code is just there and you can alter it yourself. You can add more tests as well. Now, I do have a bonus case called the algorithm confusion attack. What do I mean with that? Let's say that you have a very old situation where your API needs to interface with clients new and old. And the old client can only use tokens that are using the HS256 algorithm. Again, that means that there's a shared secret that needs to be known by all parties, because the one that signs the token uses, for example, ABCDEF as a secret, and the one that validates the token needs to also know that ABCDF was used to sign the token. This is a very bad way to sign tokens, but it has been used a lot in the past. And typically, if you would still use this, I will not ask to show your hand if you do, but if you still use this, what you would typically do is that shared secret is going to be in a key vault or in some other very protective store so that you can update it safely and rotate it at the same time. But that API also supports tokens that are signed with another algorithm, a more secure one, which uses a public-private key pair, RS256. Now, what is the algorithm confusion attack? Normally, when you post a token, you say grant type, client ID, client secret, blah, 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 you get a token back. And then your token will be signed using that private key for RS256 or the shared secret using HS256. Then your client wants to go to your API. It says, here's the token. Your API will need to find what shared secret or what public key is being used to validate it. It gets that information back, and then it validates the token and says, 200 OK, all is good. And this is where things get ugly. If your logic that verifies the token has some flaws in it, you can end up in a scenario where you can mix and match the two. So you could say, I have a token signed with HS256, but I'm going to go out to your authority because I know which authority it is, and I can find that public key that you use for RS256. And if I can somehow make your API work in such a way that I sign a token with HS256 using that public key for RS256 and make you think that you need to take that as a secret during validation. Are you confused yet? Because that's how it works. So, an attacker, again, goes out to your authority and says, hey, /Jwtks, and gets a list of keys. Cool. Now, I'm going to create my own token with HS256, and I use the key ID of that public key. And I, of course, make myself admin, whatever. I sign it, because it's just shared secret now, and your API thinks all is good. Yeah, this is explaining how that works. So, of course, the fix here is simple. If you have such a scenario, only use the key material that's relevant for the algorithm type. So, if you have a shared secret, look only at the lists of shared secrets that you have, that you may rotate. If you have a public-private key pair, only go to that JWKS URL that you trust. But of course, I can also demonstrate this. So let me go back to my code, and I have to open a different project. If I can find it. There we go. So I have a project, I have to run this to make it work. Yeah, try that again. You'll see it works. Takes a while to spin up. There we go. So I have an identity server, I have an API, and I use that identity server to issue the tokens. So far, nothing special. And if I now go into my token tool, which I have here, I just asked, I did nothing special here. This is just a simple console application that uses the token endpoint of my authority with the client ID and the client secret to get a client credentials token. Nothing special. And this is a normal RS256 token that should be, this is normal use case, so nothing hacky going on just yet. Very difficult to actually get that token out of this. And if I paste it in here, I can now try to call my API, and I have two endpoints. I have the default endpoint, which accepts both kinds of tokens, HS256 and RS256, and that works. I get a 200 OK back, and I get my weather summary back. And I also have a version 2 for the newer clients only that only accepts RS256 tokens. Again, that works. If I now pretend to be the old client, I can ask for an HS256 token using that shared secret. You can see the token is a lot smaller because the signature is only that long. But everything else is the same. So if I now copy that one, if I'm allowed by my laptop to copy the token, come on, you can do it. There we go, paste it in here. I also don't know why it decides to put it on new lines, but sure. Again, first endpoint, that works. It's now an older token, it's not as secure, but the API still accepts it. But if I try to use that on the other endpoint, it will fail because it's the wrong signature. So far, so good. But now, I can also do, and I called this HS257, and it says I used the public key with key ID and then a bunch of numbers to generate an access token. And then I generated that token. Let me already copy this, if I may. Come on. And let me first go here. So the key ID is B0C3EC and so on. If I go to my identity server, there's a discovery document which contains some information, and this one is where I'm interested in. So you have the endpoint where the JSON web keys are, which is hosted here. JKS. And this is the public key information used to validate the token. And my program, my token tool, used that information to generate an HS256 signed token. That's what I did. If I now go back into my HTTP file and I paste that token, my API happily accepts that, and it shouldn't. But this is a confusion algorithm attack in play. Of course, if I try the second one, it will still fail because it's an invalid algorithm for that second endpoint. Let's investigate that token just to see that there's nothing special going on. So again, this is my token. The algorithm is HS256, as I said, because I'm using a shared secret, and my key ID points to that public key information. Then we have the payload that you can see in there, and the signature, and all is good. In this case, I cannot validate it because I don't know on this tool what the public key is, but this works. And how does that work? Well, the tool, again, does some trickery. It goes out to my issuer, to that public JSON web key material, and it finds a key, the first one, and it uses that to create a symmetric security key to sign the token. And that's all I need to do. on this side. Of course, rest assured, this does not work if you use the default validation library out of the box. You need to do some special stuff to make this work, which is a good thing. Let me show you how to do that. Also, I should say, it's for educational purposes only. Do not use this code in production, please. Because if you do, I'm not responsible. But what happens is I have two bare schemes configured. The default one only accepts RS-256, and for older clients, I allow you to also use HS-256. And how I set that up is, so my valid algorithms are both RS-256 and HMAC-SHA-256. And here's that issuer signing key resolver method again that says, hey, whenever you need to find the public key to validate a token, use this method. And if the key ID is HS-256-1, which is my newly rotated symmetric public key, then this is the symmetric security key that you need to use. So I just generated a GUID, and then that's my shared secret for signing and validating the token. If the key ID is not that one, then you probably were using an RS-256 algorithm, so let's find the public key from the authority, which goes out to that same well-known OpenID configuration JOX endpoint, and then it finds the key material, the public key material. You can use a key ID to find the correct one, and then if you're using HS-256, return a symmetric security key. If you're RS-256, then create a standard asymmetric security key. This is, by the way, why it doesn't work by default using this library, because you have, if I just use this method, which is the typical version of how you would deserialize a JSON web key, it is smart enough to instantiate the correct type of security key. And HS-256 algorithm will not allow you to use an asymmetric security key because it's not intended to be used for that. But I deliberately, of course, for the sake of purposes here, said, if you use HS-256, I will make sure that you get the valid type of key so that my attack works. Of course, don't do this again. But this is, what I guess I want to say is, in the Microsoft Identity Model, System Identity Model, you have to do some trickery, but not every validation library is the same. So you might not need to do this trickery to make it work in a different programming language. Luckily for us, we are a bit more secure. So that was the algorithm confusion attack. And if you want to dive deeper into all of these things that can go wrong with access tokens, this QR code, and again, if you have the slides, you will also get access to this, brings you to a YouTube playlist made by Integrity, which is a security company, and they explain a lot of different kind of attacks very well, showing how to create tokens, how to replay them using Burp Suite and other tools that typical cybersecurity engineers use. I highly recommend seeing this, not to scare you, but to make you aware what is possible, so that you also know we should test against these things. And with that, I come to the end of my presentation. So if you have any questions, I will gladly take them. No questions? Yes. So you're saying to deliberately have failing tests all the time, or?
No, make it work, but make a success out of it, breaking, kind of, so you have successful tests in your pipeline.
I don't think I completely understand your question. It's me. It's me. Wait, let me go back to. Maybe I understand it better if I open the code base again.
I think he needs for it to, like, the success criteria is for it to block, to fail.
Yes.
Right?
I have two cases, if that's the question. But let me go back here. So if I open the tests, I always have one test case that says this should pass. This should be a successful HTTP request. And then I always have, and these should not be successful HTTP requests. So yeah, I do test both cases. Anyone else? A question I typically get is, are you Morgan? No, I'm not. Also, if you watch series or a movie and it says based on true events, that means that parts happened in real life, but not all of them together, fortunately for them. But the Java thing was real. So there was a Java validation library that did block algorithm none. It also blocked algorithm none using different casing, except when you used another validation method that allowed algorithm none. So it had like 3 or 4 different implementations to validate tokens, and one of them had that flaw in them. So if you were unlucky enough to have chosen that specific version of the method, then you were open to that attack. It was fixed, of course, but it was a big issue when they found out. So yeah, if there are no further questions, then I thank you for your attention.